Hello and welcome to another episode on Spiral Physics Education. This time we're going to be looking at charging by friction, and we're going to be looking at the role of electrons in charging by friction, and also introducing to the law of electrostatics and how we can demonstrate the law of electrostatics in the laboratory using some basic equipment. And we're going to finish off by explaining why it is that metal rods and objects can't be given a static charge the way that insulating materials can be. So to start off with, let's look at how charging by friction and what happens when you charge by friction. So what we normally do is we have two different types of insulators and we rub them together, and the friction that's generated allows electrons to move from one to another. And it's really important that they're insulators and that there's friction involved and that we understand that it's the electrons that move. So when we then look at the electrons, and to do that we're going to look at a little classical model of an atom in a moment, we know that in the nucleus there are protons and neutrons. So the protons are in red and the neutrons are in green. So 3 protons in this example. And if it is a neutral atom, then around that nucleus there must be 3 electrons. Don't worry about the model that I'm showing here, it's just to show you that there are 3 electrons in an orbit around the nucleus. Now, it's much easier to remove the electrons from this atom than the protons. The electrons are bound by a force to the atom that is much weaker than the protons. So you can imagine trying to get a proton out of the nucleus. It's going to be much harder, it's going to require much larger forces to be able to do that. And in fact, that will be nuclear physics. We're not talking about nuclear physics, we're just talking about static electricity. It's all about the electrons. So when an insulator gains electrons, what happens is, and you can see I've added another electron there, now this has got 4 electrons. There are more electrons than protons. So it's gained an overall negative charge. That nucleus is now negatively charged. So let's have a look at another example when an insulator loses electrons. So here we've got a neutral atom again, the same number of protons and the same number of electrons. And when we're rubbing one insulator with another insulator, let's say this one loses an electron. An electron's ripped out of its orbit and it goes off somewhere else. Now this one has only got 2 electrons, but it's got 3 protons. So it's got an overall positive charge, it's got a net positive charge. So this object, if that happened, would have a net positive charge. So when you're talking about objects becoming negatively charged, they gain electrons. And when you talk about them being positively charged, they lose electrons. I've seen students say that positively charged objects become positively charged because they gain protons. I've also seen them write they gain positive electrons. Neither of those are correct. It's either gaining electrons or losing electrons. Stick to those terms. So let's have a look at what happens in an example that we've got here. It's either an oversized comb or a very small jumper. Anyway, it's to do with 2 insulators that are involved, and one is going to be rubbed against the other. So we've got friction between 2 insulators, which means there's going to be a build-up of static charge. So if we look a little bit closer in this activity, we're going to see that they're going to start off as neutral. So that means both the comb and the jumper have got an equal number of protons and neutrons. Okay, so there's no net charge on either of them. And during the process of rubbing the comb on the jumper, what happens in this case is that we're going to say that the jumper becomes negatively charged and the comb becomes positively charged. And you can see here that I've illustrated electrons moving from the comb to the jumper. The jumper has gained electrons, the jumper becomes negatively charged, the comb has lost electrons, the comb has become positively charged. So let's look at the law of electrostatics, and we do this by a demonstration that you may or may not have seen in the labs, and we're going to just look at the equipment that's required. So we're going to need a cloth, and we're going to need two different types of plastics. One of those is a polythene rod, and usually the other one is an acetate rod, which we've got here in yellow and green. You're also going to need a watch glass, which is a bit like a glass bowl, a very small glass bowl, but upturned. So we're going to rest the rods on there. So what we're going to do is we're going to give both rods a static charge. So we do that by rubbing the rod against a cloth. And what's going to happen here is that the polythene rod is going to gain electrons from the cloth. And that means that the cloth becomes positively charged and the rod becomes negatively charged. And then we're going to get the cloth and we're going to rub it against an acetate rod. And this time, the electrons are going to go from the rod to the cloth. And that's going to leave the rod with a positive charge. So the polythene rod has a negative charge and the acetate rod has a positive charge. So then we're going to get our watch glass, our upturned watch glass, and we're going to place one of the rods on there, in this case a polythene rod. So remember, the polythene rod is negatively charged. And we're going to bring close to it an acetate rod, which is positively charged. And what's going to happen here is we're going to look at what happens to the polythene rod. And the polythene rod moves towards the acetate rod. They are attracted to each other. And because they're attracted to each other and they have opposite charges, one of the rules for the law of electrostatics is that opposite charges attract. So that demonstrates that opposite charges are attracted. So let's go back to this position again, where we're giving our different rods static charge. We've got our watch glass and we place our polythene rod, which has a negative charge on it. This time we charge up another polythene rod as well, which also has a negative charge, and we bring that in close. And this time the polythene rod that's on the watch glass moves away from the handheld one. And that means that it's been repelled. Now, because both of them have negative charges, both of them having negative charges shows that they're repelling, and that means that similar or like charges repel. And what we could do, we could put an acetate rod on the watch glass and bring in another acetate rod, so both of them will be positively charged, and we would see the same effect, that both of them would repel. And that would show then that like charges repel and opposite charges attract, which is the law of electrostatics. So let's finish off with looking at why you can't hold onto a metal rod, rub it with a cloth, and expect to give it a static charge. Well, if you were to do that, what actually happens in this case, let's say electrons move onto the metal rod. Because the metal rod is a conductor, those electrons that move from the cloth onto the rod will just be conducted along the cloth, along the rod, through the hand and away. So there's no build-up of static charge. And it's because of this word conduct. So metal rods allow electrons to conduct and flow. So they can't hold a static charge while you're holding onto them and rubbing them, because metals are good conductors. You can, however, give them something called an induced charge if you isolate the metal rod. And that's something that we're going to be looking at in videos a little bit further along in this topic. So come back to check out about induced charge, which is a little bit different from static charge. So I hope you found this video useful and helping you understand static electricity. Don't forget to subscribe to the channel and come back and visit us to get your physics understanding up to scratch a little bit better and improve those grades. And we'll see you next time on Spiral Education Physics. Goodbye.